Hello everyone, myself Sandhya Palmu. This is my current profile. These are the four standard forms in PDE. Form first, f of pq equal to 0. Equation contains p and q only. Form second, f of pqz equal to 0. Equation contains pqz. Form 3, f of xp equal to g of yq. Equation contains 4 variables. Z is absent. Today we will see form 4, f of pqxyz equal to 0. Lagrange's form. Equation contains all these 5 variables and if it is in the form pp plus qq equal to r. Degree of p and q is 1. These 3 forms I already explained in last video. Today we will see this form number 4. The general solution of Lagrange's linear partial differential equation pp plus qq equal to r, where p is a function of xyz, q is a function of xyz and also r is a function of xyz. Solution is given as f of uv equal to 0. Method of obtaining general solution. First, rewrite the given equation in the standard form pp plus qq equal to r. Second, comparing with equation, write capital P equal to, capital Q equal to and capital R equal to. The Lagrange's auxiliary equation is dx upon P, dy upon Q, dz upon R. U of xyz equal to C1 and V of xyz equal to C2 are said to be the complete solution of the system of the simultaneous equations 3 provided U and V are linearly independent. Case first, one of the variables is either absent or cancels out from the set of auxiliary equations. Case 2, if U equal to C1 is known but V equal to C2 is not possible by case 1, then use U equal to C1 to get second solution V equal to C2. Case 3, introducing Lagrange's multipliers P1, Q1, R1 which are functions of xyz or constant. Each fraction in 3 is equal to P1, Q1, R1 are chosen that P1P plus Q1Q plus R1R equal to 0. Then P1 dx plus Q1 dy plus R1 dz equal to 0 which can be integrated. Case 4. Multipliers may be chosen more than once such that the numerator P1 dx plus Q1 dy plus R1 dz is an exact differential of the denominator P1P plus Q1Q plus R1R. Combining 4 with a fraction of 3 to get an integral. So the general solution of the given equation is f of uv equal to 0 or v of phi of u. Now we will see example. Solve yp minus x square q equal to x square y. Here the degree of p and q is 1. So we will solve this PDE by using Lagrange's method. The given equation is in the form pp plus qq equal to r, which is already in standard form. Hence, capital P equal to y, capital Q equal to minus x square, capital R equal to x square y. The auxiliary equation is substitute P, Q, R, we get. So first solution, equating these first two fractions, we get dx upon y, dy upon minus x square. Considering these first two fractions, so minus x square dx, this minus x square goes to LHS, this y into dy. Integrating on both sides, we get minus x cube by 3, y square by 2 plus c1. Thus, this is first solution c1 equal to minus x cube by 3 minus y square by 2. Now, second solution, equating second and third fraction. Considering second and third, we get this x square will get cancelled, y dy minus dz. So, integrating on both sides, we get y square by 2. Integration of 1 with respect to z is z plus c2. So c2 equal to y square by 2 plus z. Thus, the general solution is phi of uv or phi of c1 c2 equal to 0. So substitute here value of c1 and c2 and this is the final solution of the given PDE by using Lagrange's method. Now second example, xp minus yq equal to x square minus y square. Again here power of p and power of q, that is degree of p and q is 1. So we will solve by using Lagrange's method. The given equation is in the form already is given in PP plus Q equal to R. So comparing, we get capital P equal to X, capital Q equal to minus Y, and R equal to X square minus Y square. The auxiliary equation is this. First solution, equating first two fractions, we get, and integrating on both sides, we get integration of this term is log X is equal to minus log Y. Here instead of constant of integration C1, write down log C1. So by using logarithmic property log A plus log B, we get log A into B equal to log C1. So C1 equal to XY. Second solution, now we cannot get cancels the fractions. So introducing Lagrange's multiplies xy minus 1. So each fraction equal to, so multiplying x square minus y square. If we multiply by minus 1 minus x square, this minus minus become plus x square. So this denominator becomes 0. 0 into each fraction is 0. Now integrating on both sides, we get x square by 2 plus y square by 2, and integration of this 1 is minus z equal to C2. Thus, the general solution is given as phi of C1, C2. That is, substitute C1 and C2, we get equal to 0. Third example, solve Ez equal to Qz plus x plus y bracket square. Solution is, we will write first in standard form PP plus QQ equal to R. So this plus Q, when goes to LHS, it becomes minus ZQ. This R we will keep in RHS. Comparing, we get capital P, capital Q, and capital R. The auxiliary equation is dx upon capital P, so z, dy upon capital Q, that is minus z, dz upon capital R, that is x plus y bracket square. First solution, so equating these first two fractions, we get dx by z, this z will get cancelled, so dx equal to minus dy. Integrating, we get the first solution C1 equal to x plus y. Now to get second solution, we cannot cancel out from the first and last fraction or second and last fraction. So here, equating first and third fraction, we will use the case that is, we will use the value of x plus y as C1. So dx by z equal to dz upon x plus y bracket square. Here's the value of C1 is x plus y. So C1 is a constant, it goes to dx and z dz. Now we can integrate. So integration of 1 is x, integration of z is z square by 2. Thus get C2 is. Hence the general solution is. Now fourth example, solve mz minus nyp plus nx minus lzq is equal to ly minus x. Here power of p and q is 1. So we will solve by using Lagrange's method. The given equation already it is given in PP plus QQ equal to R. So comparing, we get P equal to, Q equal to, and R equal to. The auxiliary equation is dx upon P, dy upon Q, dz upon R. Here we cannot cancel out the fractions. So taking the multiplies x, y, z, that is introducing Lagrange's multiplies, each fraction equal to x dx, y dy plus dz plus z dz. So introduce the multiplies in a such way that this denominator becomes 0. So 0 into each fraction is 0. So integrating on both sides, we get x square by 2, y square by 2, z square by 2. As C1, which is a constant of integration, we can adjust. So write down C1 by 2. Thus C1 is x square plus y square plus z square. This is first solution. Second solution, taking L, M, N as multipliers. So multiplying L, multiplying M, and next N, we get this LMZ minus LNY plus MNX minus MLZ plus NLY minus NMX. So this LMZ minus LMZ and this remaining terms becomes what? 0. So integrating on both sides, we get L into X, M into Y, N into Z, which is equal to second constant of integration C2. Thus, the general solution is phi of C1 comma C2. That is, substitute here, C1 is x square plus y square plus z square and C2 is Lx plus My plus Nz, which is equal to 0. Thank you.